This is the F-105D, an all-weather, single-place fighter bomber, powered by the highly reliable Pratt & Whitney J75 engine and capable of a level flight speed in excess of Mach 2. The F-105D has the armament-carrying ability of this proven F-105B, and in addition incorporates a fully integrated all-weather automatic flight and fire control system. This system consists of a sophisticated toss bomb computer, a sight system, a Doppler navigator, an air data computer, an autopilot, and a search and ranging radar to provide a means for accurate blind bombing and air-to-air attacks which is within the capability of a single pilot. Unlike other contemporary fighter bombers, the F-105 has a bomb bay, so that a special store can be carried internally and delivered at high supersonic speeds. The space in the bomb bay can also be used to carry a 390-gallon fuel tank or other equipment of equivalent size or weight. The F-105 also has 5 external stations. 450-gallon fuel tanks can be carried on the centerline station, as well as the 2 inboard stations. In addition to these tanks on the centerline and inboard stations, a 1,000-pound bomb can be carried on each of the outboard stations. Bombs up to 3,000 pounds can be carried at the inboard stations in place of tanks. Rocket pods, each carrying 19 2.75 folding fin rockets, can be carried on the inboard and outboard stations. An easily installed launcher at the outboard station permits the installation of Sidewinder missiles for air-to-air operations. Chemical tanks, fire bombs, and chaff dispensers can also be carried. A wide variety of combinations can be carried. As an example, the aircraft can carry a special store in the bomb bay in addition to external stores on all 5 stations. With a 390-gallon bomb bay tank and 3 450-gallon external fuel tanks, the F-105D has a global deployment range in excess of 2,100 nautical miles. Also, this versatile aircraft can readily be fitted with an all-weather reconnaissance pod, which makes it possible to go out and gather information for subsequent air operations. And for withering ground strafing or effective air-to-air operations, the F-105 carries the General Electric developed M61 20mm gun. The M61 gun installation in the 105 has a firing rate of 6,000 rounds per minute at subsonic and supersonic speeds at all altitudes. The F-105D has a linkless ammunition feeder with a capacity of 1,000 rounds. With the armament capabilities of the F-105 in mind, let's run through a typical F-105D all-weather bombing mission and see how easy it is for a single pilot to get conventional or special stores on target with accuracy. The mission calls for the pilot to climb to altitude and proceed over or through the weather, and then descend in a mountainous area and make a low-level penetration to the target area. He will then climb to sufficient altitude to make a blind dive toss attack, climb to altitude, and return to his base. With 3 external fuel tanks and an internal special store, the aircraft is off the ground and over a 50-foot obstacle in 5,800 feet. The pilot can manually control the climb to altitude, or he can turn the job over to the autopilot, which includes a Mach hold feature for climb or cruise at constant Mach. At altitude, he levels off and, with the autopilot still on, settles back and watches the Doppler navigator click off the miles. Before takeoff, the pilot cranked in the latitude and longitude of his home base and the coordinates of his destination, plus a checkpoint along the route. In flight, the Doppler navigator determines the drift angle and the ground speed, and through a computer, constantly calculates the true position of the aircraft in relation to the latitude and longitude set in before takeoff. The equipment operates in any weather and is accurate to 0.5% of the distance traveled between checkpoints. Let's review the principle of operation. Doppler, a German mathematician and scientist, many years ago discovered that frequency appears to change with change in relative speed. This phenomenon applied to radar beams directed ahead of, to the rear of, and to the side of the aircraft makes it possible to determine ground speed and drift angle. This information, fed into the computer, automatically solves the navigation problem and gives a present position readout on the control panel, as well as distance to go information. So far, the pilot has just been monitoring the flight and watching the numbers go by. Pre-selected checkpoints are observed on the search and ranging radar, and any error in the Doppler system can be corrected. The radar ground map or contour map mode is used to make the correction. A previously constructed radar prediction map is used to help in identifying the checkpoints. The pilot knows about when a checkpoint should appear by watching the distance to go indicator. Cross-checking the scope cursors with this distance pinpoints the location of the checkpoint. The pilot tracks this checkpoint down the azimuth cursor. When the checkpoint reaches the range cursor, he turns the switch on the Doppler control panel to fix and then back to normal. This automatically resets the navigator to the known ground position. The pilot can then put in the coordinates of another checkpoint on the Doppler navigator if required. In due time, the pilot reaches that point of the mission at which he must descend to low altitude for his penetration into the target area. However, this descent is through the weather, in an area of rugged terrain. But this is a no-sweat operation in the F-105D, since the pilot simply switches the radar to the terrain clearance mode and begins his descent. All obstructions which project above a preset warning zone below the pilot's flight path are projected on the gun sight combining glass. The projections above the warning plane also show up on the radar scope. Their range is determined from the range cursors. Elevation can be determined by adjusting the clearance plane setting until the radar return disappears. The level of the warning zone can be set to be a plane anywhere between 0 and 6,000 feet below or above the flight path of the aircraft. The pilot sets in whatever clearance he wants on the radar set, and this indication is shown on the main instrument panel. With this information before him, the pilot can let down and make a penetration in any weather with assurance that he will be alerted in sufficient time to prevent collision with the obstacle. In the target area, as determined by the Doppler navigator and radar, the pilot climbs to attack altitude and lines up on the target. He identifies the target on the scope, and by use of the antenna tilt control, determines the approximate angle of dive required. With the bomb mode selector in blind dive, the bomb nav switch is placed in the bomb position, and the nose of the airplane pushed down to the desired dive angle. The airplane is then controlled to keep the target aligned with the intersection of the azimuth and range cursors. When the solution light comes on, he depresses the freeze button and pulls up for bomb release. The bomb computer, working with the Doppler navigator for drift correction, continually computes the angle of the aircraft in relation to the required release angle for accurate delivery. When they coincide, the bomb is automatically ejected. The pilot now places the bomb nav switch in the nav position and returns to cruise altitude for his flight back to base, with autopilot set for constant Mach. He watches for his checkpoints with the radar in ground map mode. He can also monitor the flight or fly the aircraft manually by using the new integrated flight instruments. This is the latest instrumentation developed by the United States Air Force for safer flight at all speeds. Air Force and Republic Aviation pilots who have flown with this system state that a minimum of time is required for transition to these new flight instruments. The pilot is now back in the area of his home base. If the weather conditions are such as to require an instrument approach, this is also a no-sweat operation in the F-105D. The autopilot has an automatic instrument landing capability which will bring the pilot right down to the threshold of the runway so that all he has to do is flare it out and set it down. And if the landing should be in rain, a windshield rain remover is available to provide the pilot with a clear view through the windshield, as shown in this test. At a landing weight of 29,200 pounds, the F-105 can be brought to a complete stop 2,500 feet after touchdown. The corresponding ground roll without the assistance of a drag chute is 4,300 feet. So far, we have considered only one of the many missions this versatile aircraft can accomplish. Let's briefly consider some of the others. A visual identification point bombing run might be used. In this case, the pilot sets the bomb mode selector switch to visual IP and flips the ATOS switch to on. And as he comes in over his IP, he presses the freeze button and the autopilot takes over. The computer calculates the remaining run to the target. In visual IP ranging mode, the autopilot will produce a wings level pull-up at constant G to the inverted position, roll the aircraft back to normal, and head it in a direction away from the store blast at constant altitude. The toss bomb computer calculates the store release point, and when the aircraft attitude coincides with the computed solution, the bomb ejection mechanism is automatically activated. The bomb bay doors are automatically closed after store ejection. Should a low-level run on the deck be necessary in weather that goes right down to the ground, or at night, the run is essentially the same. In this case, the pilot will watch the ground map presentation on the radar scope until the IP appears. With the target, or IP, on the scope, the pilot flies the aircraft to align the azimuth cursor with the target, or IP. He continues to track the target along the azimuth cursor until the IP presentation crosses the range cursor. At this instant, the pilot pushes the freeze button to start the attack computation, and an automatic store delivery is made in the same manner as previously indicated for the visual bombing run. If the pilot cannot identify the IP, he can switch to blind TIP and continue over the target, where he presses the freeze button to effect an automatic over-the-shoulder toss. If for any reason a dive or low-level bomb release is not possible or desirable, the fire control system is capable of performing high-altitude, level, or low-toss bombing. A radar identification point is used. Range and wind data over the target is obtained from the air data computer and Doppler navigator to make an accurate release possible. Crosswind compensation is provided by the automatic roll attitude control. Another capability of the F-105 weapon system is air-to-air attack on enemy aircraft. With data link, blind ground-controlled intercepts can be accomplished. This is the combining glass presentation when the aircraft has been vectored onto the target. The horizon indicator appears as a dash line. The line around the pipper is the range indicator, while the little dot is the radar target. In visual attacks, the aircraft will be in the same spot as the radar target dot. When the radar locks on and the pilot moves in, the range indicator line will shorten. As the pilot lines up on the target, it will gradually move into the center of the pipper. With the range indicator at 6 o'clock and the target on the center of the pipper, the pilot begins to fire. When the aircraft reaches a point where a breakaway must be made to prevent a collision, a breakaway pattern alerts the pilot. Now let's look at some other features of this high-performance aircraft. The F-105D has been designed for repeated high-G missions at speeds in excess of Mach 1 on the deck without fatigue problems. Furthermore, there is no pitch-up tendency at any speed. Even in rough air, the F-105 is steady as a rock, due to the stability augmentation of its automatic flight control system, plus the inherent stability of the aircraft. 47 spins, many up to 5 turns, to both the right and left have been executed and rapid recovery demonstrated. The spin recovery procedure for the F-105 was found to be similar to that for the F-84F. The use of the emergency spin recovery chute, which was installed on the test airplane, was not required during any of the spin tests. The F-105 has provision for in-flight refueling, which is capable of filling all of the fuel tanks, both internal and external. The system has been satisfactorily demonstrated with both the KB-50 and the KC-135 tankers. Using a buddy system developed by Republic Aviation, one F-105 can refuel another at speeds up to Mach 0.9 at 35,000 feet. Structural tests on the F-105D accomplished to date have confirmed that the design requirements have been met or exceeded. The F-105D was designed to sustain flight loads of plus 8.67 Gs and minus 3 Gs at subsonic speeds, and plus 7 Gs and minus 3 Gs at supersonic speeds. Armament tests in many configurations have been successfully accomplished. 750 and 1,000-pound bombs have been dropped, as well as fire bombs. Chaff dispensers and rocket pods have also been carried. Internally carried special stores have been satisfactorily released at supersonic speed at both low and high altitudes. Level flight releases have been made at Mach 1.73 at 35,000 feet. Sidewinder missiles have been fired at speeds up to Mach 1.5. The F-105 retains a high G capability at 40,000 feet for excellent maneuverability. During gun-firing demonstration tests, 7 flights were accomplished in one day, over 7,000 rounds being fired. Many other proving operations have been conducted. Tests on snow-covered runways in Alaska demonstrated that the aircraft can be easily taxied and parked by use of differential braking and nose-wheel steering. Other low-temperature tests in the Climatic Projects Laboratory, as well as in Alaska, proved that the F-105 is highly suitable for Arctic operation. Average takeoff distance, for example, was 2,600 feet on hard-packed, snow-covered runways. Likewise, tests on wet runways have demonstrated that the aircraft can be fully controlled even under these conditions. Flight experience with the F-105 drag chute installation indicates a 99% reliability factor. And for emergencies, barrier engagements have been tested successfully, as shown by this slow-motion photography. Certainly it has been demonstrated that the F-105 Thunderchief is a versatile fighter-bomber capable of performing many all-weather missions well within the capabilities of a single pilot. The question may well be asked, what has installation of all this automatic equipment done to the mission availability factor of the aircraft? Or, in other words, what has been done to assure that the F-105D will be available for mission after mission? The problem of availability was considered right from the start of design. For example, the complete all-weather capability of the aircraft required the integration of many communication, identification, and navigation units to conserve space and make maintenance easier. This design study resulted in the uniform packaging of the units into what is known as the CNI package, standing for communication, navigation, and identification. But knowing that some malfunctions will occur even in the best of systems, accessibility was a primary concern in designing the airframe also. systems which may require maintenance are readily available, and those that may require replacement are easily replaced. The gun and the linkless ammunition feeder are readily accessible. In addition to the reliability and accessibility designed into the aircraft and its components, complete ground support equipment is available to maintain the aircraft in a ready condition. For example, for ground checking the hydraulic system, quick disconnects, readily accessible, are provided for rapid connection of an external hydraulic pressure source without disturbing the airborne hydraulic system. A standard maintenance trailer capable of adjustment on all three axes is used for aft fuselage section and engine removal and installation. Engine removal and installation rails are provided as ground support equipment rather than as an integral part of the aircraft structure. Therefore, aircraft performance is increased by not having to carry around this unnecessary weight. Also, with a single engine aircraft, the number of man-hours of maintenance per flight hour is less than with multi-engine aircraft. Equipment is provided for checking the electronic components on the flight line. Here is a typical unit. With this test set, for example, the autopilot system can be rapidly checked for operation and accuracy by qualified line personnel. Expertly trained electronics technicians are not required for this test and replace type checkout equipment. Should one of the testers give a no-go indication, the component can be removed and an operating unit from stock readily inserted so that the aircraft will soon be back in commission. To check out the entire communication, navigation, and identification electronic system, a low-powered, self-contained, radiating facility is furnished that requires no operator after being started. With this unit, called RADFAC, the CNI systems in each aircraft may be accurately checked for operation within 90 seconds. Should one of the subsystems prove inoperative, the design of the equipment is such that removal merely requires disconnecting the antenna lead, loosening one thumb screw, and pulling out the unit. Replacement with a serviceable unit is just as simple. The unit can be checked out on the appropriate check bench, the defective part located and replaced. After the repaired unit has been tested, it can be placed in stock ready for use as a replacement unit. Because of the emphasis on maintenance during design of the aircraft and its subsystems, and because of easy access to system components and adequate ground support equipment, a minimum of maintenance time is required to keep the F-105 airplane in the ready-to-go condition, and normal servicing operations are equally as efficient. Because of the convenient height and accessibility of the bomb rack, personnel can easily and comfortably install a bomb or fuel tank. The ejection mechanism is also used as a bomb hoist. And because the F-105 can be started with a cartridge starter, no external sources of power are required with their time-consuming connections and disconnections. The airplane can be maintained in alert status at the end of the runway without a large complement of personnel and equipment. And most important of all in these uncertain times, the F-105 weapon system is a proven design and reliable. There have been no power plant failures in over 2,300 hours of flight accumulated by the F-105 with the Pratt & Whitney J75 engine. Extensive flight testing has proved that it is a stable platform through all regimes of flight. Structural tests have proved its rugged construction, and the equipment required for all-weather ground and air attacks by a single pilot has been incorporated. The Republic F-105D Thunderchief is in production and will soon be delivered to operational squadrons of the United States Air Force. Last but not least, the F-105 still has growth potential. It's a supersonic, all-weather fighter bomber that's in being, tested, and ready to deliver the Sunday punch for the air forces of the free world.